Hello everybody, this is day 2 of 11.3 and the last ever screencast of the year. Woohoo, we made it. Today we're going to talk about z-score or z-value. Again, very, very important in statistics. All right, so recall normally until now we were using box plots in order to compare two different sets of data values, right? Sometimes it's also important to not to compare two different sets of data, but to compare two data points within the same set. Okay, so if you have two people with different heights, right, you want to compare where they fall in terms of the average. All right, for that, we use what we call a z-score or a standardized value. The z-score tells us the number of standard deviations a given value is above or below the mean. All right, so if I know what the average height in a certain population is, and then somebody comes and tells me I am, this many feet tall, I can tell them, oh, you fall right within two standard deviations of the data, of the mean, and so on. So that's what it is. The z-score is calculated using this cute little formula right here. Z is z-score, and it's x minus x bar. So x is your data point. Remember, x bar is the mean. And then the sigma here is the standard deviation. And we have to round z-scores to 2 decimal places. I want to make sure to let you know that in some places x bar is used for the mean, and then other places it's the mu. These ones are pretty basic. There aren't very, complicated calculations here. So here it says find each of the following. Find z if x is 24, x bar is 29, and sigma is 4.2. It's just a simple plugging in. So z is x minus x bar over sigma. You can't mess up the order of the x and the x bar, right? So z is 24 minus 29 over 4.2. Okay, z is negative 1.19. All right, you see how the order makes a huge difference, because here we got z equals negative 1.19. What does that mean? That means if I have my normal distribution and this is the mean, this data point falls 1.19 standard deviations to the left. So if this is 1 standard deviation and this is 2 standard deviations, this data point falls 1.19 to the left. So it's somewhere over here. All right, so that negative makes a huge difference. All right, let's take a look at this one here. Now we want x, and we've got everything else. So again, we start with our cute little formula. All right, so what do we have here? Z is negative 1.73, and that equals x minus x bar, 48, over 2.3. All right, so I'm going to multiply both sides by 2.3. So x minus 48 is negative 3.979. Go ahead and, go to some more decimal places here. Add 48. So x is 44.021 when I plug it in my calculator. Now, where do we round? You have to round to the same place value as x bar. So because x bar is an integer, no decimal places, we also say x is 44. All right. So I don't know what happened with my formatting here, and I didn't catch it in time, but this problem here actually needed a lot more space, and somehow there isn't that much more space here. So you know what I'm going to do is I'm going to take example 4 and I'm going to put it at the very bottom of this here. We're going to do it here. All right. So this is where example 4's solution is going to go. All right, let's just read what example 4 says here. Consider a comparison of two individual data values as we try to determine which is more extreme. The 76.2 inch height of a man or the 237.1 pound weight of a man. Okay. So we've got two different data points here, right? And we want to know which is more extreme. Which is the more extreme value? Is it a man who has a 76.2 inch height, or is it the man that has a 237.1 pound weight? And when we say extreme, okay, we're not being derogatory, we're not putting anybody down, we're just saying which one is farther from the mean for that specific statistic. Okay, we obviously cannot compare the two values directly because that's like comparing apples to oranges. What we have to do is we have to compare them by finding their corresponding z values. So we have to compare the height to the mean of the heights of men at that age group, and then we have to compare the weight to that mean. So here we are given some samples. For men, the heights have a, let me color code. The heights have a mean of 68.34 inches, and the standard deviation is 3.02 inches. The weights have a mean of 172 and a standard deviation of 26. So what we're going to do is we're going to find the z-scores of each of those data values. All right, so first, let's do the z-score of the height, and I'm going to label it z sub h. Okay. The data value that we're looking at, it's a man of 76.2 inches minus the mean for the heights was 68.34 over the standard deviation, 3.02. And that has a z-score of 2.60. Remember, z-score has to have two decimal places. So that particular value is 2.6 standard deviations away from the mean. All right, so now let's do it for the weight. The z-score for the weight is 237.1 minus 172.55 over 26.33, and the z-score for that is 2.45. So that one is closer to the mean than the 76-inch height. Therefore, the height of 76.2 inches is more extreme. Okay? All right. So now let's move on to example number 5. Here we need to find the interval of z values associated with each given area. And we're going to write the process by hand here. But basically, let's take a look at what A wants. A wants us to look at the middle 50% of the data. So here I have a normal distribution. The middle 50% is this, right? That shaded area is the middle 50%. Okay? Now, I want to know what is the z-score at the edges of this here, okay, for the middle 50% of the data. What are the z-scores? So how many standard deviations away are these boundaries here? Okay, so let's take a look at this for a minute. If this whole thing is 50%, that means how much do I have for the outer edges? I have 50% total for this and this combined, right? Because if the shaded purple is 50, then the outside is also an additional 50. Okay, if the outside, the red parts together are 50, how much is each red part individually? 25%. So that means by the time I've come to this point here, I've reached 25% of the data. And then the purple part is an additional 50% of the data. So by the time I've come here, I've reached 75% of the data. Okay? All right. So now I'm going to use my calculator to figure out what is the z-score at the 25 and the 75% mark. That means how many standard deviations is that? Remember what we talked about before? We said if we had gone one standard deviation away on either end, that green part would have been 68% of the data, right? But now this is a smaller portion. It's only 50% of the data. So what is the standard deviation at those red marks? Okay, so what we're going to do is this. On our calculators, we're going to write this down here. We're going to press Menu in the scratch pad. So let me show you here. We're going to press Menu and then Statistics, right? So let me go here, Menu, Statistics. And then we're going to go to Distributions. And from there, from Distributions, we're going to select number 3, Inverse Normal. Okay. Once you press inverse normal, it's going to ask you for the area. Here, we're going to input our boundary percentages. Okay, that means, what is the first boundary percentage here? 25%. So I put 25% and I get, wait a minute. Let's do that again, sorry. So we're gonna go to Menu, Statistics, Distributions, Inverse Normal, and I'm sorry, we have to put the decimal, not 25%, but 0.25, enter, and there you have it. That's negative 0.67. So we say, so this one is negative 0.67. And then I have to do it again now for this one. So let's go one more time. Menu, Statistics, sorry, Distributions, Inverse Normal. Let's put 0.75. And now we get 0.67. And that makes sense because it's symmetric, right? So remember how I said at the green mark, this would have been 1 standard deviation to the left, 1 standard deviation to the right. Now these are further, like closer in. So it's only 0.67 to the left and only 0.67 to the right. Okay, so how do we write this then? We want an interval of z values. It has to be an interval. So we say, because this is the region in between negative 0.67 and positive 0.67, I say negative 0.67 less than or equal to z less than or equal to positive 0.67, meaning z is in between these two numbers. Okay, it's very similar to how we wrote the way back in the day before the quarantine, when we did those inequalities, right? How we used to do the number line, and then we would say like minus, plus, minus, and then depending on if it was this region, we would say less than, or we would bound it, or we would say less than or greater than. Same situation. Okay, here I want the outside 20% of the data. So let's draw again. And if I want the outside 20%, that means I want this and this to add up to 20 together. If I want them to add up to 20 together, how much is each part? 10% and 10%. Right? That means by the time I've come here, so basically if I start at the very left where I have 0 of the data points, and then I walk inwards, here this is 10% of the data points. And then if I keep walking, how many percent of the data points have I accumulated at that point if I have only 10% of the total left? Well, this is 90%. Okay? So between so if I want the outer 20%, it's the stuff under 10% and over 90%. Let's go back to the calculator. All right, now you can do a couple of things. You can either do that whole process again, or if you're just repeating, you press up, highlight this one, press enter, and then you could just go in here and just edit and say 0.10, negative 1.28, and then I do that again. So up, enter, left, 0.9, 1.28. So now this region here, okay, these are going to be broken up. This region, this has a z-score of less than or equal to 1.28. And then I say, or this region here has a z-score greater than or equal to 1.28. And there you have it. You can go ahead and start on your homework. If you have any questions, you can ask me during bonus or during class. I will be more than happy to go over this stuff again. Until then, have a great rest of your day. You are done with the recordings for this year. Woohoo!